Okay, welcome to Computer and Network Security. Our lecture this week is going to be on symmetric encryption. So to start off, just some questions getting you to start thinking about encryption and how we actually apply this in the real world outside of computer and network security. Think about these questions. Should eavesdropping be made illegal? Should it be illegal for people to stand outside of someone's door without them knowing and listen on their conversation? Should it be illegal to overhear someone's phone conversation, whether that person is in public or private? Should it matter if there's a reasonable right to expect privacy where the person is standing? The second question, should speaking a different language than the primary or native language in a country be made illegal? In the United States, we have many different languages spoken, and many people don't understand a lot of the languages that are being spoken. Should people be able to speak in that language, or is this somehow some sense of security or a way that people are able to speak without other people understanding? And should there be laws in place for this, or is this more of an ethical issue? If you're out at a restaurant with people who don't speak maybe your native language, is it okay for you to speak in that language around them? Of course, the legal aspect and the ethical aspect are probably two different issues here, but we would like to think that ethics sometimes drives the law. Okay, our outline for today, we're going to talk about symmetric keys, what symmetric key encryption is. We're going to talk about some attacks of symmetric key encryption and some of the different algorithms like AES that exist that uses symmetric key encryption that we still use quite frequently. Okay, so to start off, here is a diagram, and this just kind of shows what symmetric key encryption works. So let's say that we have Alice who is transmitting some message to Bob. So Alice types some message and wants to transmit it to Bob, and if Alice doesn't want anybody else to be able to read the message that she transmits to Bob, she can encrypt it with a secret key. Now, with symmetric key encryption, the key that Alice uses to encrypt that message is going to be the same as the key that Bob has to use to decrypt that message. This is symmetric key encryption. Our next lecture is going to be on asymmetric key encryption. And with asymmetric key encryption, there's a different key which is used for encrypting as opposed to decrypting. Today's lecture, though, is on symmetric key. The key that Alice uses to encrypt the message is going to be the same as the key that Bob uses to decrypt the message. So you see the secret key, which is shown here in the diagram here, and over here is going to be exactly the same. Now, hopefully that secret key remains secret. We need two people to keep that key secret. We need Alice to keep it secret, and we also need Bob to keep it secret. If either one of them reveals that key, or if that key is compromised on either end, then anyone who has that key is going to be able to decrypt the message and get the data back out of it. So Alice types a message, encrypts it with a secret key, sends it across a public network where anybody can read what's being transmitted across the internet, the public network. However, it's encrypted, so no one's going to know exactly what it says unless they have the secret key to be able to decrypt it. Then Bob gets the encrypted message on his side. He decrypts it with that same secret key, and that gives him the plain text back out in the message that he has been able to read. Some definitions of some of the terms that we use with cryptography and symmetric cryptography. Plain text is the original unencrypted message. So this is the message. The plain text is the unencrypted message. Once we encrypt it, then it is called ciphertext. That is what we send over the public network. The algorithm that we use to encrypt it is called an encryption algorithm. The algorithm that we use to decrypt it is called a decryption algorithm. We have a shared secret key that goes into both the encryption and the decryption algorithm. It's used for both encrypting and decrypting. A cipher is the encryption and decryption algorithms themselves. Those are called ciphers. And a key is the set of values on which the cipher operates. And we're going to see some cipher algorithms here in just a few minutes, and we're going to see the different keys that go into them. It's very, very important when we have encryption and decryption functions that this behavior stands. When we encrypt plain text P with some encryption algorithm with a key K, we get ciphertext. When we run that ciphertext into a decryption algorithm with that same symmetric key K, we need to get the plain text back out. If we do not, then we don't have an inverse operation and we don't have a symmetric key algorithm. So we need to make sure that these are inverse operations. The bottom bullet there, that third one, shows you the inverse operations. If we encrypt some plain text X with a key K, and then we decrypt it with a decryption algorithm with the same key K, it's the same as if we did it the other way around with the encrypt and the decrypt algorithms, and ultimately we should still get our plain text X back out. One of the most difficult problems with symmetric key encryption is how do we exchange the secret keys? We need to make sure that Alice and Bob have the secret keys, but nobody else has the secret key. Well, we obviously can't transmit the secret key in plain text across the network because anybody who's sniffing it is going to be able to get it. So how do we actually get the secret key over to another computer? One easy way, this may seem like a naive way to do it, but it's an easy way and it's a very secure way, is that you manually take it over there. Instead of trying to transmit it over a network, there's no reason why you can't put it on a USB drive. You walk it over to another computer and you load that symmetric key onto that computer. So physically taking a key from one computer to another is one way that we can securely transmit symmetric keys. Now we're going to see with asymmetric key algorithms another way that we can transmit keys back and forth with trusted authorities, and we'll see that in our next lecture. One principle which is extremely important when we're talking about any of these encryption algorithms is Kirchhoff's principle. Kirchhoff's principle says that at any node in an electrical circuit, the sum of the currents flowing into that node is equal to the sum of the currents flowing out. Oh, wait a minute. That's Kirchhoff's law. For those of you electrical engineers or people who have taken EE classes, hopefully you saw the humor in that joke. Kirchhoff's principle, different from Kirchhoff's law, similar in how we say it, however, completely different principle. Kirchhoff's principle, assume that the enemy knows the algorithm. The resistance of the cipher to attack must be based on the secrecy of the key. What Kirchhoff's principle says is make everything public except the key. We want to make the algorithm public. We want you to know exactly how we are encrypting and how we are decrypting. And we are so confident that our algorithm is that good that even with that, you will not be able to break our algorithm. There are many encryption algorithms out there that currently abide by this philosophy. The best ones, the algorithms are completely public. You can look up AES, symmetric key algorithm. You can look up RSA, an asymmetric key algorithm. You can see exactly how they work, the exact algorithm, all of the math that goes into them, how the keys are generated. However, you aren't able to crack it if you're given the ciphertext without knowing a little bit more about the key. Okay, another definition here, just distinguishing between cryptography and cryptanalysis. Cryptography is the science and art of creating secret codes. This has been around for thousands of years, back to the days of Caesar, of Julius Caesar. Cryptography has been around. Cryptanalysis, on the other hand, is the science and art of breaking those codes. As long as cryptography has been around, cryptanalysis has also been around because people want to break those codes. They want to figure out exactly what are these secrets that people are trying to say, what are they trying to tell, and why do they not want us to know. So cryptography came around saying, hey, let's create these secret codes, and then as soon as that came around, then other people said, gosh, I want to know what's inside of that, why won't they tell us? And then cryptanalysis came around. So these are two very, very popular fields. There's a lot of mathematics that goes into these fields. We're going to go through some of it today. We're not going to go through some real heavy mathematics. If you read the papers that I have posted, though, you'll see a lot of heavy mathematics inside of it. It's not difficult to understand. There's just typically a number of steps to get from the beginning of plain text to the encrypted text and how you encrypt and decrypt with the different keys, generating the keys, and so on. Okay, now what are the different types of attacks that we have? So now we are encrypting. We have our encryption algorithm, we have our decryption algorithm, we have our secret keys also on both sides. It's a symmetric key algorithm, so we have one key on each side. How can we attack this? How can we try to get out what the data is without knowing the key? Well, one way to do it is if we only have access to the ciphertext. This is typically the case. We encrypt our data, we send it across the public network, and other people can get the ciphertext. However, from the ciphertext, they don't have the key, they don't know anything about what the data is, so it's going to be very difficult for somebody to get the plain text back out of that. That would be a ciphertext only. This is probably the most secure that we have right now because we don't have any idea what we're going to be able to do to get the plain text back out. So this is the typical case when we're transmitting data encrypted along a network. Now the next case is a little bit more sophisticated, where we have a little bit more information here. It's the brute force case. So what we have here is that Eve, our eavesdropper in the middle, has the ciphertext, which she already has, also has the algorithm. Okay, well, we're going to be using AES. Okay, now she knows a little bit more about the data that's being encrypted and transmitted, and also the key domain. Okay, well, it's a 256-bit key. Okay, this is a tremendously large key. However, if Eve knows the what we're transmitting, the ciphertext, knows the algorithm we're using, let's say AES, and also knows the key domain, 256 bits, it narrows it down a lot more than if Eve only had access to the ciphertext. Now she has a little bit more realm of the domain of how she can try to get the plain text back out. This would be the exhaustive key search method. The reason it's called brute force, she would have to go through and try every single key that is in that domain. Now this is a very, very large number of keys. However, depending on how sensitive the data is, it might be worth it for her to go through every single one of those keys and see if she can get the plain text back out just by decrypting using all of the different keys that exist in that domain. The third bullet there, the statistical attack. The statistical attack is a really interesting one because it takes advantage of understanding what letters are used most commonly in different languages. In the English language, E is the most commonly used letter. So when you are looking at the ciphertext that's being transmitted, if each character individually was being encrypted, you might be able to figure out what letter in that ciphertext is E, because you would just see the same combination of characters in the ciphertext relating back to the plain text. So that would be a statistical attack. That's just one of the terms, meaning that E is the most commonly used character. However, there's also strings of characters that are used very commonly. We don't typically have more than 3 consonants together before we have another vowel. So there's a lot of statistics that can go into just the language itself to figure out a little bit more about the plain text that's being transmitted. Now, our last 3 there, the known plain text attack being the first one, and the chosen plain text and the chosen ciphertext, is where Eve is getting a little smarter. She knows a little bit more about what's being transmitted so that she can maybe even figure out what the keys are. So assume in the known plain text attack that Eve has access to both the plain text and the ciphertext, and she just doesn't know what the key is. Well, if she knows the algorithm, she knows the ciphertext, she knows the plain text, and she knows the key domain, she might be able to get the key back out of it. There still are a lot of combinations of keys. However, for a sophisticated attacker, she might be able to get the key back out. So it's important now that this is not known. The way that she would be able to do this most likely is if she's compromised one of the computers, but she hasn't been able to get the key. So if she's compromised Alice's computer and she's able to send out a known plain text, and then she just intercepts the ciphertext that's been transmitted, then she might be able to determine the key going backwards, knowing that she's got the ciphertext and the plain text, both knowing the key domain, knowing the algorithms being used for the symmetric key encryption. The chosen plain text attack is similar to the known plain text attack, but now she's able to send her own keys. So this is what I was talking about with the known plain text attack. So now she's actually able to send out multiple plain texts, and she gets all of the different ciphertext for each one of them. So maybe the first one that she sends out is just A, and then the second one is B, and the third one is C, and she sends it for all 26 characters, and then she sends AA, and then AB, AC, AD, and so on. She gets the ciphertext for all of those. Well, when you start piecing all of this together, you're going to have a much better chance of being able to come up with what that secret key is that's being used to encrypt and decrypt the data. The chosen ciphertext attack is just the opposite of the chosen plain text attack. So now we're going to assume that Eve has access to Bob's computer and can send ciphertext, and then she intercepts what the plain text is, so exactly the opposite. So those are getting a little bit more sophisticated. She's had to compromise some computers to be able to get access to those, but when she does that, and this is where our lecture from last time comes in, if you have malware, viruses, and so on your computer, that this is some of the things that they're able to do, is that they can encrypt with the keys that you have on your computer and transmit it. It's going to act as if it's coming from you, but then they might actually even be able to get the keys, even if they're not able to get it based on how they have compromised the security on your computer. Here are a few ciphers that we are going to talk about. Now remember, a cipher is nothing more than just the encryption algorithm. One of them is a substitution cipher. This is just replacing one symbol with another. So instead of sending the character A, you're going to send the character D. We're just going to move everything 3 characters to the right. So if you're going to send an A, you're going to send a D in its place. If you're going to send a B, you're going to send an E in its place. If you're going to send C, you're going to send F in its place. This is just a substitution cipher. Not really much going on there. A transposition cipher substitutes one symbol for another, but instead changes the location of the symbol. So instead of sending out the string ABC, where A is the first character, B is the second, and C is the third, maybe what we're going to do is we're going to send BAC. Where B, even though it's the first character that appears, we've transposed it where it's actually the second character in the plain text. And A, which is the second character in the ciphertext, is actually the first character in the plain text. This actually is very, very effective. It's hard for humans to figure this one out. Once you know the algorithm, of course, it's very, very easy. Computers can detect this one really quickly. However, humans have a hard time doing this one just because we can't transpose in our minds as quickly as computers can. So that one actually works very well if you're not dealing with computers and you're just dealing with people, that you can use the transposition cipher, and it's going to take them a little bit of time to be able to figure out what the code was, the plain text was from ciphertext that you've transmitted. The third one is a block cipher. That's where we take a group of plain text symbols of some size greater than 1. We encrypt them all together to form a ciphertext of the same size. So now, instead of encrypting each character individually, let's encrypt the first 3 characters as one. And then let's encrypt the second 3 characters as the second character, and so on. When we start doing things like this, obviously the key set that we're having to generate is going to have to be much larger because we're taking a combination of 3 characters and just generating a single character from it. However, if we have this large range that we're transposing it over to using the block cipher, it makes it a lot more difficult for us to be able to decrypt it without knowing what the key is. Okay, looking here, this is a specific cipher. It's called the veneer cipher. And I'll show you how this one works. We'll walk through this one with a specific key. So what we have here is we have all 26 characters in the English language up here along the top of the table. We have the 26 characters in the English language along the left side of the table here. And then you see that we have the alphabet in these rows and columns also, and they're just kind of transposed a little bit. So it starts with A here, and then a B here, and goes through where we have A at the end. It starts with a C in the third row, and goes through where we have a B at the end. So we've transposed them slightly in the middle there. Now, if I want to encrypt the key comp E, I'm going to have to encrypt it with a specific key. In this case, I'm going to encrypt it with a key which is me. The key is going to be ME is my key. So the first thing that I do is I look at my letter C and I pair it up with the first letter in my key, which is M. So I'm going to look for C, M in my table. So I find my C right here. I go all the way down to my M, which is right here, and I find what letter's in that cell. And you see that I have the letter O. So what I've done is I've taken my C from comp E, taken my M from my key me, and it generated the letter O. Now next I'm going to take O from comp E, and I'm going to pair it up with E from me. So I take O from comp E, pair it up with E from me, and you see that the letter is S. So O with an E gives me an S. Next I have M in comp E. Now you see that my key ran out, so what I do is I just keep duplicating it. So I go back to the beginning, which is another M, so I have M paired with an M. So here's my M. I go down to my M here, which is a Y, so you see M with an M gives me a Y. The P with an E, here's my P, I go down to E, you see that I have a T, and then my last one, an E with an M, here's my E, I go down to my M here, and it gives me a Q. So what I transmit is OSYTQ, and that would be comp E encrypted with a veneer cipher with the symmetric key me. Now, on the other side, to decrypt this, what I do is I have to go the other way around. So I have my O, and I know that this was encrypted with an M. So I look for M in my column, and then I go out and I find where the O is. You notice that each character only appears one time in this row. So I go out here, I find my O, and then I go up and I see what character is at the top, and you see that it's a C. So when I have my O, which is my encrypted text, and I pair it up with my key M, and I get a C back out of it. So now here, with my S, so what I'm going to do is I go to my row E here, and I need to find what column has an S in it, which you see is right here, and then I go up to the top of that column, and I see that the second character is O. So now I've got my C and my O of comp E. You can follow similar steps and you can decrypt it back out. So you see that I'm still using the same key. It's important that that key remains secret though, because if the key me gets out, then it's going to be very easy if the person knows, if Eve knows that we're using the veneer cipher and she knows that the symmetric key is me, she's going to be able to decrypt that encrypted text very, very easily, just as we just did here. Okay, here is the transposition cipher. This one is keyless. All that we needed to know here was that we had 4 columns. And so you see the ciphertext that we're transmitting, MMTAEEHREAEKTTP. And now all we had to do here is you see that I was writing it up and down in rows. So we did MMTAEEHREAEKTTP. I know it sounds like an eye chart. However, when you write it out that way, now it's very, very easy for humans to read. You see it says, meet me at the park. So it was easy for us to read that as soon as we just put it in the right order. However, looking just straight at the ciphertext, I don't know how long it would have taken us to figure out what that was. So that's just a transposition cipher. It's very difficult for humans. However, a computer can easily just start testing different combinations and figure it out if we think that we're just using a transposition cipher there. Okay, one effective means of encrypting is going to be to combine ciphers. If you combine the transposition cipher with the veneer cipher and possibly use some other different ciphers in there, you're making this even more difficult for somebody to break. However, you have to keep in mind that we want to continue abiding by Kirchhoff's principle, meaning that the algorithm is going to be public. So if we are encrypting with multiple ciphers, we want to let the other people know this is what we're doing. We don't want security through obscurity. What we want is we want them to know this is how we're doing it, and we have enough faith that we have done it so smart that you are not able to break this. So if what you find yourself doing is the way that this is working, the best way it's working is that nobody else knows how we're doing it. That's probably not a good algorithm. You want other people to know, you want other people to try to break it. These different security algorithms we're talking about here have been around for 20, 30, 40 years, and people still haven't been able to break them. Those are good because those algorithms are known. It's known exactly how they work, the math is known, the algorithms are known, how the keys are generated are known. However, even after all of that, we still haven't come up with a way to do it in any real amount of time. Brute force is one of the fastest ways to do it. We have a few other heuristic algorithms for trying to break some of these. However, there is no known fast way of going about breaking them, at least not one that has been published. So here is AES. This is the Advanced Encryption Standard. AES requires a block size of 128 bits, 3 different keys, sized 128, 192, and 256. So it uses 3 different keys for encrypting and decrypting. It's an open algorithm. Go online, look up AES. The Advanced Encryption Standard. The way that it came out in 1997, the National Institute of Standards and Technology began looking for an algorithm. They wanted to find an advanced encryption standard to use. They called it AES. So they opened this up. There was a competition. There were a number of algorithms submitted. There were about 12 of them that made the final cut. And out of those 12, one of them finally made the name AES, and it was by these researchers here, Damon and Ridgman. They had originally called it Rindale, but that is now the algorithm which is used for AES. And there are a number of other algorithms. DES, which is just the Data Encryption Standard, was the first version. AES was the second version of this. There are a lot of different encryption algorithms out there. This is just the one more popular one. It's the one that the federal government in the United States decided to standardize on. And so it has been used for a long time. 1997 is when they started looking for this. In 2001 they standardized on this, so we've been using this algorithm now for quite some time. We'll talk about some more algorithms when we get to our next lecture on the asymmetric algorithms, which are used quite frequently, especially with secure HTTP. We do use symmetric key algorithms. A lot of times we use symmetric key algorithms for remote login. So if you SSH into a server, you most likely are going to be using a symmetric key algorithm for transmitting the data back and forth. And this is why if you use PuTTY or one of those other programs, the first time that you connect, it pops up a security box and says, oh, are you sure that the authentication of this key can be verified? And that's because this key was transmitted back to you in plain text most likely, And so it's just making sure, are you sure that you really want to accept this? Because if somebody else intercepted this in the middle, they're going to know everything that you're doing. And of course, we always just say yes, but the first time that you get a key and you remotely log into a server, it's probably best if you're on a known network, you're on a local network, and you're not doing it over the internet, so that just in case somebody happens to be snooping while you are connecting for the first time and transmitting keys, that they're not able to get the key while you do that. Okay, last questions here for today. Just to keep in the back of your mind and think about these. Do you think that symmetric key algorithms work better for wired or wireless transmission, or do you think it matters? So with wired versus wireless transmission, the difference is who has access to it. Even with wired transmission, if you don't have control over the entire wire, there's a chance that somebody is eavesdropping in the middle of the wire, or somebody is listening to a router that wire is going into. So there's not really much of a difference. The only difference is with wireless transmission, you don't have to have physical access to the wire, but you could just be sitting near the transmission. So it's not going to matter for symmetric key algorithms, whether it's wired or wireless. They're still going to work just the same way over a wired or wireless network. The second question, symmetric key transmission secure? Do you think it is easy to hack? Well, the security of a symmetric key encryption algorithm remains in keeping the symmetric key private. As long as that symmetric key stays private, it is going to be a secure algorithm. If that key gets out, though, then it is not going to be a secure algorithm anymore. So the responsibility lies in both the receiver and the sender, because they both have the same key. If either one of them gets compromised, then the security of the algorithm will be at risk if that key is able to get out. All right, hope you enjoyed this lecture. Our next one is going to be on asymmetric key algorithms, and I will talk with you all then.